Section 4.7, inverse trig functions. What we're going to do is we're going to use our understanding of the unit circle to evaluate inverse trig functions. So we'll be working backwards from the exact values. A couple things going back to inverses that we've previously done. A function is one-to-one if every distinct point of the graph has a different y coordinate. So every point has a different y coordinate. So what that means is a function is one-to-one if it passes the horizontal line test. So we already know that in terms of passing the vertical line test, it tells you whether something is a function or not. But if it passes also the horizontal line test, then we know that the function is one-to-one, which means every point is distinct. No repeat in the x or in the y. So on example 1, is the graph a one-to-one function? So this is an exponential, y equals 2 raised to the x power. Is this graph a one-to-one function? So as you graph and draw these horizontal lines in, is there any point where you can draw a horizontal line where it intersects the graph at more than one place? And even as you get down to the bottom here, remember that's getting closer and closer and closer to the x-axis. So at no point does it ever intersect twice. So is this graph a one-to-one function? And the answer is yes. Number 2, which is the stuff that we're about ready to talk about, y equals cosine of x. So you can see, and this is just part of the graph, that there are going to be all sorts of places where you can graph a horizontal line and it's going to intersect in multiple places. So your cosine graph and your sine graph are not one-to-one functions. So that's what we're really going to be focusing on in these notes. So this one is no, it is not a one-to-one function. And then your equation y equals x, which is linear, is yes, it is a one-to-one function. So there are plenty of functions that we have learned that are one-to-one, but there are also some that are not, such as a quadratic is not one-to-one, which is what we focused on a lot from Unit 1. And what we have to do, we had to restrict the parabola to just one side of it. And that's really what we're going to be focusing on with the trig functions as well. Alright, on this slide we're going to look at y equals sine of x. So you can see the sine curve that we have here, and you can see all the ordered pairs that are placed on there, the typical ones that we have in terms of graphing these, where we have our middle, max, and min. And then you can see the x-coordinates are your radians. So the domain of a sine graph, we have talked about many a times, is negative infinity to infinity. You can plug in any value of x that you want for the sine curve. The range, though, we only get values from -1 to 1 back. Okay, so your domain and your range. Is the sine graph a one-to-one function? Well, no, it repeats. You can just look on the x-axis alone. It repeats all over the place. So what we have to do is we have to restrict the sine graph so it is a one-to-one function. And we can do this in a couple of places, but there's really one place that is that really everyone uses in terms of inverse sine. So we're not going to start at 0, because if we start at 0 and go up and then go back down, it repeats right there. So what we're going to do is we're actually going to go back 2 intervals right here at negative pi over 2. So from negative pi over 2 all the way to pi over 2 is where we're going to restrict our graph. So we're going to get rid of all this other stuff. So we're going to basically, if I can do this, take all this other stuff out that we don't need. Same thing on the other side. We're going to restrict this to be a one-to-one function. So I'm going to erase all these other things. And we're only going to focus on those x values from negative pi over 2 to pi over 2. And so our domain has now changed for the inverse, and we're going to use only negative pi over 2 to pi over 2. That still covers your range from -1 to 1. So you never lose range values when you restrict your domain, all right, in terms of inverses. So what does the inverse of sine function look like? Well, we can actually write it 2 ways. On your calculator, it will typically be written as y equals sine with the -1, because that represents the inverse. But another way that you will see this is y equals arc sine of x. So arc sine of x is just another way to write the inverse of a function. All right. So now here is the graph of the arc sine of x, or inverse of sine here. And so you can see, and if you remember from what we've done before, the domain and range of an inverse switch. So the x becomes the y becomes the x. The domain becomes the range becomes the domain. So the domain of our sine graph with its restriction was negative pi over 2 to pi over 2. So therefore, our domain, or our range now, for the inverse will be that same thing. So from negative pi over 2, and I'm using brackets because those two values, those two angles of x, are included. And then your range, which was negative 1 to 1, now becomes your domain. So this is your inverse sine function when you graph it. And so you can see on the graphing calculator down here below, you have the sine graph, and then in red, and then in blue you have the inverse. And remember, it's supposed to be reflecting over the line y equals x. So you can kind of see, and once again, the blue one is restricted because it's an inverse. So we had to restrict the original. So if you kind of cut that off in terms of your sine graph there, you can see that those two parts reflect across the line y equals x. So a lot of information about trying to understand this. When we go to answer inverse sine functions, you're going to be given the domain, but you have to answer using the range, which is now your angle. So before, you would have to tell me what angle it was. Now you have to tell me the value for that. So you're going to be given the value, and then you're going to have to write the angle of that. Okay? So I think I said that backwards, by the way. So you'll be, when we originally did this with exact values, you had to find the value. Now you're going to be finding the angle measure. So let's take a look at a couple of these. Okay, so the arc sine of x is an angle whose sine is x. The values of the inverse sine function are in radians. This is very important. All of our answers will be in radians. We will not write any of these in degrees. So with the unit circle, we now know, if we go back and look, this is pi over 2, and down here is negative pi over 2. So all of our inverse sines are going to fall on this part of the unit circle. All right, which covers all values from 1 to negative 1. That's your range right there. All right, and then remember, now that's being switched. So now this represents your domain. So it says find the exact value of inverse sine of 1. So I'm giving you the value, and you need to give me the angle. So what you're trying to answer is sine of what angle is equal to 1. Now before there used to be a bunch of answers, but we made it a 1-to-1 function, so you're only going to give me the angle between negative pi over 2 and pi over 2. And there's only one value that happens. So you need to think about the ordered pair when y is 1. Okay, what ordered pair is that? That would be at pi over 2. So the ordered pair for pi over 2 is 0, 1. So therefore, the angle that gives us a value of 1 is pi over 2. And there's no other angle that does that. For example 2, you have arc sine of negative 1/2. So what is that going to give us here? We're looking at, all right, well, once again, what you're trying to answer is sine of what angle is negative 1/2. So when you're thinking about this, remember, looking at the y value, what ordered pair, what angle gives you an ordered pair of 1/2 on your y, which would make your x square root of 3 over 2. So that would be pi over 6. That's your 30 degrees. So pi over 6, but it is a negative 1/2. So that would not be in quadrant 1. That would have to be in quadrant 4, okay, because it's the negative. So this answer would be negative pi over 6. So what is sine of negative pi over 6? Negative 1/2. And then for the third one, I'm going to change this to a positive so we get a positive in here on this one. So inverse sine of square root of 3 over 2. So once again, the question you're trying to answer is what angle for sine gives you positive square root of 3 over 2, which means your ordered pair is square root of 3 over 2 for y, which would be x would be 1/2. What angle is that? That would be pi over 3. And since it's a positive, it will be a positive angle at pi over 3 in quadrant 1. So that's how inverse sine functions work. You're not going to give me more than one answer for each of these because you're only going to give me that the range value in this case for sine would be negative pi over 2 to pi over 2. All right, so now we look at cosine. So you have your cosine graph here. the original domain is negative infinity to infinity, and the range is negative 1 to 1. So we're basically going to do the same thing we did for sine. Now cosine's a little different, because if you go from negative pi over 2 to pi over 2, that is not a 1 to 1 function. All right, that would be right here. So that same domain for sine has to change for cosine. So we're actually going to start cosine at its max and then go down to the min, and that will be from 0 to pi. So we're going to change the domain to make it 1 to 1 between 0 and pi. Range will not change. You don't want to lose any of the y values. So I'm going to do the same thing I did the other one. I'm going to basically erase the rest of the graph that I do not need. So we'll cut all this other stuff out. Same thing on this side. Alright, so now when we do the inverse of cosine, or arc cosine of x, the domain is now values between negative 1 and 1. And then the range, we restricted originally the domain for the original function, is now 0 to pi. So your answers will now be from 0 to pi. And then I went ahead and did the same thing with the inverse of cosine in terms of the graph and reflecting it. Once again, it's kind of hard to see, but you have the inverse, and then that reflection is going to be over here on the other side. And so once again, that the equation reflects over the line y equals x, the inverse does. So let's take a look at a couple examples. So in terms of the unit circle, cosine goes from 0 to pi. So we are only looking at this part of the unit circle. So with cosine, cosine is positive on quadrant 1 and then negative in quadrant 2. So find the exact value of arc cosine of 0. Once again, what are you thinking? You're thinking, okay, what angle gives me an x value of 0? Alright, well, at pi over 2, your ordered pair is 0, 1. Over here, it's 1, 0, and then at pi, it's negative 1, 0. So only at that one value right here, at 0, when x is 0, gives us an angle of pi over 2. So arc cosine of 0 is equal to pi over 2. Alright, inverse cosine of negative 1/2. So, once again, what is it that we're thinking? We're asking ourselves cosine of what angle is equal to negative 1/2, with the restrictions in place, obviously. And so the ordered pair we're looking for is negative 1/2 comma something, which in this case for your y value be square root of 3 over 2. What angle gives you that ordered pair? Well, that will be pi over 3. Now it is a negative though, so we want the angle in quadrant 2 that would give us that pi over 3. So pi over 3 would be in quadrant 1. That same angle of pi over 3 in terms of its reference angle would be 2 pi over 3. So inverse cosine of negative 1/2 would be 2 pi over 3. So if you said what's cosine of 2 pi over 3, you're hopefully going to say negative 1/2. That's what we're looking for. C, once again, I'm going to change this negative to a positive. Let's go ahead and look at the positive square root of 3 over 2. So what's the ordered pair? Well, let's first think cosine of x is equal to square root of 3 over 2. The ordered pair would be square root of 3 over 2 for your x. Y would be 1/2, which means you're looking at an angle of pi over 6 at your 30 degrees. And since it is positive, it will be in quadrant 1, so therefore your answer is just pi over 6. Alright, let's go ahead and look at our last one for tangent. So tangent will do the same thing. So tangent in terms of its domain, we know we have a lot of restrictions here. So your domain, as we had talked about before, is x such that, and then you would say x cannot equal, and so for, you can see your vertical asymptotes start at pi over 2, and then occur every period, which is pi. So plus pi n, and then once again where n is an integer, alright, and we'll obviously put restrictions on that, and your range was all real numbers. So when you look at your tangent one, where are we going to place those restrictions? Well, if you look at the original tangent that's between negative pi over 2 and pi over 2, from here to here, that covers all the y values. So that's really where we're going to go. We're going to cut out all the other parts of the tangent one where the vertical asymptotes are, and they create another period. So we're going to do the same thing we did earlier. We're going to basically erase all the other stuff that we do not need. So we'll start here and take all this other stuff out, and then on the other side we'll do the same thing. And so now we're going to restrict the domain to include all values between negative pi over 2 and pi over 2, but not including negative pi over 2 and pi over 2. We're not going to include those because those are your vertical asymptotes. So that's different than what we had done back on your sine graph. Your sine graph does include those values because they do exist, whereas tangent, they do not. So you need to be careful of the difference between those two. And then once again, here's your inverse of tangent. So your domain will now represent any value, all real numbers, so negative infinity to infinity, so that's all real numbers. And then your range, we're only going to include the angles between negative pi over 2 and pi over 2. Once again, those two values do not exist, though. So you can see the red lines are all your tangent graph, and then the blue one right here represents the inverse of tangent. And that once again reflects over that line y equals x. Alright, so let's take a look at a couple examples for inverse of tangent. So for the inverse of tangent, we're going to do the same thing that we did for sine, but we're not going to include, because those are undefined, from negative pi over 2 to pi over 2 on your unit circle. I'm going to put an open circle here and here because those values create vertical asymptotes, and so therefore we will never write pi over 2 or negative pi over 2 for any of our inverse tangent expressions. So find the exact value. So here we go. Now with tangent, remember, is y divided by x, so it's a little bit harder in terms of the ordered pair. But when tangent is 1, your ordered pair was square root of 2 over 2, square root of 2 over 2, because when you divided those, you would get 1. It is a positive 1, so that means you're going to be up here in quadrant 1, so therefore the angle is a 45, but we're going to write it in radians, so it's pi over 4. Arctan square root of 3 over 3, so tangent of, once again, what we're going to think is tangent of what angle gives us this value. Now, this one's a little bit harder unless you remember, what angle keeps giving you square root of 3 over 3. We'll figure this out now, though. Square root of 3 over 3, if you look at, you got really one of two choices, square root of 3 over 2, 1/2, or the other one. If you take y divided by x, or sine divided by cosine, I wrote that wrong, so let me fix it. 1/2 divided by square root of 3 over 2, the 2's would cancel and you'd be left with 1 over the square root of 3, which when you rationalize it is square root of 3 over 3. So that would be our ordered pair, which relates to a 30 degrees or pi over 6. Now it is positive, so we do want to stay in quadrant 1, so that would be pi over 6. Okay. On C, we went inverse of tangent of negative square root of 3. So now we're going the other way and getting tangent of x is equal to negative square root of 3. So our ordered pair is going to switch to 1/2 square root of 3 over 2. One of them is negative, though. And this represents basically the other one, which would be your 60 degree or pi over 3. So this one you'd be taking square root of 3 over 2 divided by 1/2. The 2's cancel, and that's why you get the square root of 3. But it's negative. Now remember on this one, I didn't talk about this earlier, but we're not going to go all the way around and write the angle as 5 pi over 3. 5 pi over 3 does not fall in between pi over 2 and negative pi over 2. So we're not going to go in that direction. We have to go in this direction to get that angle. So therefore, the answer to this is going to be negative pi over 3. And so that's why you have to pay attention to, there's different ways that you can write the angle, but for tangent, it has to fall between negative pi over 2 and pi over 2. So make sure that you're not writing, once again, you're not going in the wrong direction there and writing it as, 11 pi over 6 or 5 pi over 3 or 7 pi over 4 or whatever. You got to go in the negative direction to get that angle. So that's it with our inverse trig functions. Sine, cosine, and tangent is what we looked at today. We'll look at the other three on another video. So to finish up here, these are the 3 important things that you must know when we go and do inverses of our trig function. So arc sine, the answers have to be from negative pi over 2 to pi over 2. Arc cosine is from 0 to pi, and then arc tangent, same as sine, but negative pi over 2 and pi over 2 are not included because, remember, those are undefined for tangent.